Hey algebra friends, here we are. We're looking at section 5.2. We're going to talk about slope and its relationship to this idea called direct variation. A little weird, but we're going to talk about slope. I mentioned in the last video how slope is a variable m, and oftentimes we're going to see equations in the form y equals mx plus b, where m is being multiplied with x and b is something called the y-intercept. This will come later, all right? So I'm going to put it in a thought bubble and say, I'm thinking about it. It'll come later. What I want you to know is that direct variation is very similar to this, except the b thing isn't there. So direct variation is defined as a relationship between two variables where one variable is equal to k times another variable. Okay, you can think about this like so many things have this kind of relationship. You think about going to a store, right? If you go to a store, the amount of money you spend, right, buying, I don't know, let's say one bag of bags of apples. Let's do this, bags of apples. So the amount of money you spend buying K bags of apples will directly vary depending on the number of bags of apples you buy. You dig what I'm saying? So for instance, let's say the bag of apples costs $5 per bag, $5 per bag, right? And I tell you that I'm going to buy 6 bags of apples. You would say, well, 6 times 5 is 30, lady. And I'd say you're right. And notice that the amount of money I spent is it changes directly with the number of bags of apples that I buy, right? The number of bags of apples being 5 in this case. And this 6 here, this K value, is considered the constant of variation. It is the constant of variation. Let me use my fancy highlighting skills. What? So my constant of variation is that K value. In our example, it was the price of the bag of apples. So direct variation is the relationship between this whole thing here is direct variation. It is the relationship between two variables, in this case y and x, where one variable is equal to the basically multiple of the other variable, and that multiple being the direct variation, the constant of variation. The next concepts that we have here, we're not going to deal with directly a whole lot in this particular section, but it's going to be so important as we move through our algebraic and also just honestly math relationship, math history, math journey for the next several years. So family of graphs refers to graphs that have a similar characteristic, right? So right now I'm going to draw a graph, XY axis, and I'm going to start off with what I'm going to call the most basic direct variation equation, which is y is equal to x. Can somebody tell me what the K value is here? I hope you saw that it is 1. Good. So the direct variation relationship here is just as y changes, x change. We get the y equals x line, which is this perfectly, I'm not doing a perfect job right now, but it's this perfectly diagonal line that travels through the x-axis, not the x-axis, travels through the origin here. And so this is that, right? When I start changing things, like if I said, well, y is equal to 2x, here the constant of variation being 2, now my graph will change a little bit, right? It'll have a steeper kind of a slant like that. Still going through the origin, but that's what it is. And then let's try another one. Y is equal to negative 1/3 x. You didn't think I'd go fractions, did you? But I did. All right, so we've got, it's always going to go through the origin when we're dealing with direct variation equations. And then it's going to go, let's say, what is it? Up 1, back 3. So something like this, and over 1, down, And so we got this situation here for y is equal to negative 1/3. And notice the constant of variation is very similar. In fact, it is the slope, right? It is the slope. Notice that all of these graphs would make what we would call a family of graphs. This is a family of graphs. And the parent graph is going to be the main one, the main guy. I should have did it in red because that's the parent graph. The parent graph is this guy here, the one that it's in a sense, sometimes I think about the parent graph as if something is as a parent and all the children have similar qualities but not exactly the same. Or you can think of the parent graph as like the standard and all of the other graphs are like riffs on it, right? So it's like you're kind of adding and subtracting, doing some other little extras to it. So we're gonna use this concept a lot, even though we're not gonna talk about it a whole lot in this section. All right, let's go ahead and take a look at some examples. So this example is entitled Slope and Constant of Variation, and so what we're going to do is we're going to do what they asked us to do. They said, hey, name the constant of variation for each equation. So you remember this tells me that I have direct variation situation. K is the constant of variation. So name the constant of variation. Yes, sir. Yes, ma'am. The constant of variation for this one, right, is going to be 3, right? And the constant of variation for this one is going to be -2. Yay! And then the next thing they say is then find the slope of the line that passes through each pair of points. Well, I think I already let the cat out of the bag, didn't I? Because I said, well, slope and constant variation are the same, and they are. And so this is just an opportunity for us to really just say, yes, yes, it is. So let's go ahead and do our thing. We can find the slope. Slope is equal to y sub 2 minus y sub 1 over x sub 2 minus x sub 1. And so when I do that, I see, let's say I'm going to call this my x1 y1, and this therefore is my x sub 2 y sub 2. So I get 3 minus 0 over 1 minus 0, and not surprisingly I got 3. Similar thing will happen over here when I do the change in y over change in x thing, or use this formula to find the slope. And so I can say that this be my x sub 2 y sub 2, and this by x sub 1 y sub 1, just to change it up a little bit. So I have 0 minus a minus 2 over 0 minus 1. 0 minus a minus 2 is 2. 0 minus 1 is -1. And again, I got -2. We are not surprised that we got the same thing, but it was nice to see the confirmation. So I've taken the liberty to draw a pair of x and y axes here, and taking the opportunity to plot the points there in green. I was only able to get these 3 guys there, but that's okay. You get the idea. And when I draw my line through, I get a linear equation. I can see I have a line. That was so horrible. I'm sorry. I can't even let it stand. I mean, you know, you got to do your best. Can you guys hear that wind howling? It is a windy day today. All right, so with this in mind, this is what I get. This is how we graph it. Not too bad. Okay, so again, we have an opportunity to do direct variation, a graph of a direct variation relationship. They're showing us that k is less than 0. We can look at it as the slope is less than 0 as well. What did I tell you that all direct variations have in common? You remember when we had our graph up here? Let me go back up to our beginning. All of the graphs go through the origin. That's like a staple. That is key. That has to happen. And so now, as I go back down, sorry about that, as I go back down to this example, I know that one of the points will go through the origin. Now I can make a table like last time, and I'm probably going to do that example too, just so we have it. But what I want you to see is that we could also use this k value as a slope to find a way to migrate around this plane to find the other points. So we talked about slope as being the change in y over change in x, and -1/3, we had a fraction situation before where I said you can literally throw the fraction, the negative value up, or you can throw the negative value down. So I can like write it as like 1 over -3. And you can use this as almost a map to direct your migration from point to point. What do I mean? Well, here, looking at it this way, this map says go down 1 and go to the right in the positive direction on x. Remember, change in y over change in x. So if I go down 1 and to the right, 1, 2, 3. I didn't mean to do that dot. Let's not make dots. 1. If I go down 1 and to the right, 1, 2, 3. This supposedly is another point on the line, that on this direct variation line. And then I could look at it as go up 1 and go to the left in the negative direction for x, up 1 and to left 1, 2, 3. And this is giving me a line, and the question is this the line that I'm actually going to get if I were to plot points? So let's go ahead and plot points. Let's figure out our x and y axis and see what's going on. So if I put in 0, and let's try -3 and +3 and plug in and see what we get. Well, when I plug in 0, I get 0, so I know that the origin one was fine. And if I plug in a -3 times a -1/3, I get what? Negative times negative is a positive. 3 over 3 is 1. I get a +1. And when I put a +3 in there and multiply by this -1/3, well, a negative times a positive is going to give me a negative, and 1/3 times 3 is 1. I get that. Let's go and see if it jives up with our machinations from where we were using the slope as kind of a map. It's kind of marching orders. So 0, 0 is cool. Positive -3, 1, 2, 3, +1 is also cool. And a +3 and -1 is also excellent. So those 3 points work whether I were to choose it by using the slope. I don't like that. For me, I make mess. Whether I was going to use it, find it by using the slope or by, by using x and y points and plugging them in. So here's a little bit of a summary of what we talked about. When k is positive, we're going to go up to the right. When k is negative, we'll go up to the left. Very similar, or exactly the same as when we talked about slope. These next examples, we're going to write and solve direct variation equations. So suppose y varies directly as x. So that tells me, as soon as you read that line, that tells me y equals k times x. So y varies directly as x can be translated literally into this. Okay, so they gave us that, and they said that y is equal to 28 when x is equal to 7. Write a direct variation equation that relates x and y. So we want to know how all of the x and y's in this direct variation equation relate. Well, basically the key is we need to solve for k. And to solve for k, we need to get k by itself. We're going to divide both sides by 7, and we get that k is equal to 4. Now that we found the constant of variation, we know how all the y's and x's in this particular direct variation equation relate to one another, and they and they relate to each other in the following way. So y equals kx, and then we are going to write y equals 4 times x. I'm going to put a box around that because this is the answer. Let's look at this next one. Use that direct variation equation to figure out x when y is 52. No problem. This is simply a substitution situation for us. We're going to plug 52 in right there, set it equal to 4x, and then we're going to solve for x. Solving for x is no problem. 4 times a number is going to give me 52, so I'm going to have to divide both sides by 4 to figure out what that number is. And when I do that, I get that 4 goes into 52. What is that, 13 times? 4? Yeah, I got 13 times. So in that case, x is equal to 13. Right, so a flock of snokies here in example 5, we learn migrate at a rate of 375 miles in 7.5 hours. Write a direct variation equation for the distance flown in any time. So the distance is going to be my y and the time will be my x, and I got to figure out what that k value is. So what I'll do is I'll put 375 is equal to k times 7.5. You know this. We're going to find out our k value by dividing both sides by 7.5. And when we do that, we get that k is equal to 50. The next thing we need to do is finally write the equation. And so the equation, given any time and any distance, given for any time, whether it's 2 hours, 5 hours, 7.5 hours, it will be y, the distance covered, would equal k, in this case k is 50, times x per mile, 50 miles per hour in a sense is what that refers to. Graph the equation. I know you guys love graphing with me. I'm not going to graph this one. I think you know what to do. We're going to do an XY axis. We're going to either plug in some points and substitute, but given time constraints, I won't do that now. Let me know if you have any questions. If you need to see it graphed to understand, we'll do it. But I think we can skip that for now. And I look forward to talking to you guys soon. Take care. Bye bye.